ChatGPT is amazing. It can write poems, it can do mathematics, and it can even be an agent. But if we think about it, back in the days when we had things like Siri, Google Assistants, or even Google Translate, it wasn't that amazing. I mean, Google's Google Assistant, Siri, they always mess things up. And Google's Translate, it also mistranslated it. What happened? What changed? How did we went from Siri to ChatGPT? The difference is modern AI have attention. I mean, literally, like in 2027, a new paper released. It's called Attention is All You Need. And it introduced a novel architecture called Transformers. That was a revolution. That's what changed AI from always making mistakes and being horrible into what we have today. Before talking about transformers, let's talk about what we had before. Before transformers, we had architectures such as LSTM and RNN. So this is the architecture of an LSTM, and as you can see, it has a long-term memory and a short-term memory. And the thing with LSTM is they are really sequential. Now, first, let's try to send this text through the LSTM. So as you can see here, we have a node. You can think of this as some kind of a function that takes long-term memory input and the short-term memory and outputs a new output with updated long-term memory and the updated short-term memory. The LSTM has different weights inside it, and depending on those weights, all the input, long-term memory and the short-term memory will be updated. Now, if we send I, first the input will be 3. And because it's our first run, we can say long-term memory and the short-term memory is 0 because we didn't send anything earlier and our first word is I. And after it processes it, it gives an output. Let's say the new output is 4. And the updated long-term memory is something like 1 and the short-term memory is something like 2. Now, let's send the second word of our sentence, 2. And after we send the 2, it will use the updated long-term memory and the short-term memory to change the input into a new output. Let's say the new output is something like 6. This is LSTM in a nutshell. Actually, the real architecture is way more complicated. It's something like that. But for this video, I think this way is way more intuitive and easy for us to make a mental model. To sum up what we said, what LSTM basically does is it takes an input, sends an output, and it also keeps a state, which is a long-term memory and a short-term memory. And throughout the whole text, the long-term memory and the short-term memory updated. This is how older model used to have context. They use this memory state to have context about the previous tokens you send. Training big AI takes large amount of time and computational resources. And because of the LSTM sequential nature, it's really hard to train huge models with things like LSTM and RNN. The other issue is it's using a long-term memory and a short-term memory to keep the whole context. If the text is really large, like a whole book, it will really struggle to put all the context into those short-term memory and the long-term memory. Also, LSTMs can't learn from the context. What that means is, if you tell ChatGPT an example or even how to do it, it will do that task very well. But for the LSTM, that's not the case. LSTM processes text from beginning to the end. Because of that, the LSTM can go to the beginning and take a look at and be like, oh, there's an example, and according to the example, I should give a result like this. That's why newer models like ChatGPT can learn from the examples you give. And back in the days, things like Siri and Google Assistant didn't able to do that very well. We discussed limitations of LSTMs and other previous architectures. Now, let's discuss how transformers manage to fix these issues. Core of transform architecture is attention. Think of it as attending to every word you send at once. Every token you send to the model is represented as a vector, which means every token has a bunch of numbers that represent what the word is. What an attention head does is it updates the token representation based on the specific relationship between other words of that whole text. An attention head has 3 matrices. They are key, query, and value matrices. The query is basically, it's like a question. It's basically what the token is looking for. What other tokens that are relevant to that specific token. And key matrix is like an index. It tells what the token is about. So let's try to calculate attention of the word cat. First thing it does is it tries to find out what are the all other tokens that are most relevant to token cat. This is done by taking the query of cat and multiplying it with all the keys of all other tokens. In this attention head, the goal is to find the adjective of a certain token. And as you can see, the adjective of cat has a higher attention score compared to all the other values. Attention is the sum of all attention scores multiplied by the value matrices. In here, it's 4 multiplied by 2, adding with 4 multiplied by 1, and doing it to all the values. So here, attention of the word cat is actually 14. So what it did was it updated the word cat based on all other words in the whole text. We can think of it as before the attention head, the word cat represents just a cat, and after this attention head, it starts to represent a black cat instead of just a cat. In a transformer, this step is done by multiple attention heads at the same time. As an example, this attention is used to find the adjective, and there's another attention head, and this would be used to find the owner. And in this attention head, the attention score for things like I will be higher, and for words like have, black will be really low. Changing the representation of the token cat into telling this is not just a cat, there's an owner for the cat, and the owner is I. Every token inside an attention head is attending to every other token parallelly, and also each attention head is running parallel to one another. This is the superpower of transformers. Everything is really parallelized. And the thing with all the modern GPUs they are really good at doing parallel tasks. Because of that, we can train large model really efficiently and really fast compared to our previous architectures such as LSTM and RNNs. Another interesting thing about transformers is they scale really well. As an example, if you think about it, the GPT-3 or GPT 3.5, they have really less parameters compared to newer models like GPT-5. The thing is, transformers tend to get better and better the more training data and the bigger the model is. Because of large training size and the context size, the models are really generalizable. They can write articles, do mathematics, and even be your agent. Another really interesting thing is, at scale, transformers tend to show emergent behaviors. Best example is chain of thought. When the model divides the question and prompts itself, it shows really good improvements in areas such as science, mathematics, and other areas that requires a lot of logical thinking. Now you know why modern AIs are really good compared to our previous predecessors. So I think if we further want to improve transformer-based large language models, what we need is to improve our transform architecture.